Hi everyone, I'm Gavin Yeung. Today I'm going to talk about my research about developing MZO emitters for emerging cattail-based solar cells. First, why do we use solar cells? Solar energy is the most abundant renewable energy resource that we can access, and we can harvest this kind of energy using solar cells. Cattail solar cells has a low material usage, so it is a leading thin film photovoltaic technology. Cattail also has an ideal bandgap for a single junction solar cell. The current record is 22%, and in theory, it can reach over 30% efficiency. Due to the material usage, it is a low-cost leader with over 10 gigawatts installed worldwide. This work is a collaboration between Colorado School of Mines CSM and Colorado State University CSU. So I'll first break down into our device geometry. In CSM, we first sputter deposit a 100 nanometer MZO on top of a commercially available Tec-10 substrate. We then send our samples to CSU for their processing. That includes a 500 nanometer CST and a 3-micron cattail. The question for this research is what makes the best MZO for this device structure and how to make these MZO. So in CSM, we sputter deposit MZO using the sputter 2 setup as shown in the right figure here, with the magnesium and zinc metal target sitting diagonally, and on the side we have a gallium oxide target. We reactive co-sputtered MZO that provides a faster and cheaper deposition method compared to single ceramic MZO target. We are able to make combinatorial libraries with zinc rich on one end and magnesium rich on the other end for screening MZO compositions. We will then make uniform MZO films to refine the performance in devices. We are able to sputter GMZO films with the addition of gallium oxide targets, and gallium is used for doping, and in combinatorial libraries we will add a gallium gradient on top of it. For more details about GMZO doping films, you can refer to my paper in the JVSTA. So why do we use MZO? MZO has a couple benefits that includes its transparency, and the conduction band and bandgap of MZO can be adjusted by the magnesium content. If we increase the magnesium content, we increase the bandgap and the conduction band of MZO. It also forms a good chemical passivation in cattail absorber that have a high carrier lifetime. It is possible to dope with group 3 elements, for example, as we discussed before, using gallium. There are a couple challenges using MZO. MZO is fairly insulating, so it will not benefit group 5 dope cattail absorbers. It also has concerns about stability that we have resolved it using reactive co-sputtering method. Emitter-absorber interface is important for the device to perform better. The emitter aims to reduce the interface recombination, which is a product of interface recombination velocity and the hole concentration. An ideal conduction band offset has a 0.2 electron volts difference that reduces the hole accumulation at the interface and reduces the recombination. If the conduction band offset is too low, the hole will accumulate at the interface and increase the recombination. That will reduce the voltage in the JV curves, as shown in this purple and black line. If the conduction band offset is too high, we don't have a hole accumulation, but we will have an electron barrier at the interface that minimizes the flow of electrons that increase the series resistance and create this S-kink in the JB curve. In previous work, we have used MZO in CdTe devices, that we are able to achieve 16% efficiency across multiple platforms, in CSM, in NREL, and in CSU. This demonstrates that our reactive co-sputtered MZO is stable and robust. The optimal MZO bandgap in CdTe devices are 3.55 electron volts with a window of 0.1 electron volt. This is consistent with the model predicted that we have a small window of optimal conduction band offset. In this study, we have shifted gears from CdTe to CST absorbers. Looking at the top SIM profile here, after device processing, we create a graded selenium content in the absorber and a maximum of 30% selenium. Going to the bandgap diagram here of CST, it shows that we're at the minimum bandgap of CST with around 30% selenium that aims to increase the current collection without losing the voltage. Looking at the conduction band of CST, we see that if we increase the selenium content, we keep reducing the conduction band energy, and also it is expected that we will reduce the magnesium content in the MZO emitter to create an ideal conduction band offset. In a preliminary screening, we have employed a 3-inch square combinatorial library of MZO to make 25 devices. We have a zinc ridge on one corner and a magnesium ridge on the other corner. This result is very promising because we are able to make over 70% efficiency in this library. This also suggests that the optimal bandgap of MZO in CST devices is slightly higher compared to CdTe absorbers. We then fabricate uniform MZO to optimize the CST device performance. The MZO bandgap is between 3.68 and 3.92 electron volts, and the JV parameters on the left shows that they are statistically identical over this range, with mean JSE around 28 mA per centimeter square, VOC around 850 millivolts, fill factor over 77%, and efficiency over 18.5%. Compared to CdTe absorbers, these sets of experiments contradicts our expectations because the magnesium content is higher and the device performance is insensitive to the magnesium content in MZO. Our champion device, after optimization, were able to reach 19.5% without an anti-reflective coating. To date, this is the highest number reported using the MZO CST device structure. In conclusion, we have employed reactive co-sputtered MZO in CdTe and CST absorbers. In CdTe absorbers, the MZO optimal bandgap is 3.55 electron volts with a small window of optimal bandgap that follows our expectations and simulation results. In graded CST absorbers, the optimal MZO bandgap window is much greater with a higher magnesium content of 3.8 electron volts. We are still exploring why these two phenomena could happen. Throughout all the optimization, we are able to achieve a device performance with 19.5% efficiency. Here, I would like to thank my colleague in CSM and my collaborators in CSU. And I would also like to thank NSF to fund this research. This is the end of my presentation. Thank you.